All right. Welcome everybody to Class 1. I need you guys to get here on time because this is ridiculous, but hey. All right, this class is called Shock and Awe. Yes, you'll understand why in a little bit, why it's called Shock and Awe. But first, let's go over a few things. If you have a smartphone, I want you to go ahead and go to pollev.com. This is, we're going to have some interactive polls and questions. And if you have a smartphone, you can go right to this website, pollev.com. And when you get there, you'll see a screen that looks something like this, and you want to go ahead and click on I'm participating. Once you get to that screen, you're going to go ahead and join a presentation. Go ahead and put my name. So go ahead and write Valentino, that's Valentine with an O at the end instead of an E, Z, and go ahead and click Login. And when you do that, you should see this page here. It should say something as soon as your presenter displays a poll, will automatically update. So as soon as I go ahead and push a poll and make it live, you'll see it on your screen. So let me go ahead and make a poll live. And now on your screen, you should see an interactive poll, which will look like this. Oh, let me close that. Who is your favorite singer? And you can vote, and I can see some of you are voting already. Okay. Oh, Joe's getting some hits. That's nice. Okay, but anyways, you get the point. If you don't have a smartphone, you can actually text as well. You text all the text messages go to 22333, and your response is just the number there. So if you want to vote for Bridget, you're going to go ahead and type in 664650. So you're going to text 664650, the number, text it to 22333. All right, everyone get a knack for that? Okay, moving on. Removing our faith hat. What does this mean? In order to really absorb this material, we need to, as a people of faith, take our faith hat off and put our science hat on. We need to do this to be able to fully absorb the revelation, and once caught, we can put our faith hat on. Now, what do I mean by this? I've talked to a lot of people about this before, did some test runs on some family members, and I noticed that, you could talk to someone, let's say you're talking to a Christian who knows nothing about the atom, and I break down how the atom is made of a proton, a neutron, and an electron. How everything is made up of atoms. Atoms are still the fundamental building blocks as a whole for everything in our universe, and that they're made up of three things. Three, but one. Okay, well, I'm expecting like, oh, wow, that's pretty profound, But, someone with their faith hat just like, oh, yeah, okay, yeah, that's nice. Like, really? That's the best you can do? That's nice, So I really need to take our faith hats on and put our science hats on, because I need you all to think like scientists so that you can really catch the revelation. And then once the revelation's caught scientifically, then we could put our faith hat on and start applying the word to what we know. For example, here's a test. If a giant metal orb fell from the sky and landed 5 feet above the ground in a levitated state, what would you do? Meaning, would you immediately wonder what kind of force is holding the orb in the air? If this really happened, and this orb was just floating there, would that be your first thought? Like, wow, what kind of magnetic force is this? Is this some type of alien spacecraft? What type of energy is what's up with this technology? How is this occurring? Or if you immediately fall to your knees, pray the rosary, and you're in awe how angels are able to hold the orb in the air on their shoulders, you know what? This class is probably not for you. If you start praying the rosary and like, ay, Dios mío, look, I'm looking for people that have a little bit more scientific mindset, if you know what I mean. Simple example. So how can we know what type of science to trust? Now, we all know evolution's garbage, and all scientists stand by that 100%, so why believe anything? Well, first, not all scientists actually stand behind evolution. There's a surprising growing number of scientists, your typical ungodly atheist scientists, that think evolution is as much garbage as most. Now they're going towards the creationists and aliens made us, but you sort of get my grip, you know. The point being is, if we all know as Christians that evolution's garbage, and those of you, there's a lot of you in this room that have been through mentorship, know the weakness of that, then it starts to call into question, you know, character. You know, in a court of law, all you have to do is disparage a portion of someone's character, showing that they have a habit of lying, and it doesn't matter what they say, you're not going to believe it. Well, it's the same principle here, and I think that's why I'm going through this, is so that we need to restore some type of balance, because we can't just dismiss everything, but we certainly can't trust everything either. So my answer is we have to. All of our technology and medicine is based off of science, meaning we can't just randomly pick and choose what to believe and not believe without being informed. We need to be able to make educated and informative decisions before rushing to judgment. We'll go into examples later where you can see literally how hypocritical we can be, where we can rush to say, oh, you obviously don't know what the heck you're talking about. That doesn't make any sense to me. When the fact of the matter is, your technology on your phones, the technology that if you're watching this now, this is all mathematics. It's all mathematics, it's all calculus, it's all based off of physics. And you're wondering how this ties into physics. Well, you'll understand that by the end of the class. So I'm going to go through some tests. And this is what I'm going to do. You, the audience, you are the scientists, all right? Obviously, if you pass the first test of the orb, you know, you have a scientific mindset, but we need to test your logic because, you know, it's been a while since some of y'all have been in school. There are some solid, wacky, and questionable scientific thoughts and reasoning out there. So we need to know what's solid, what's questionable, what's wacky. Many things scientists claim seem to be either true, or they're blatantly false, or they're exaggerated. You're going to see this a lot, where scientists take one thing and they run with it, you know, like evolution. And they do this for either their own motives, either political motives. When you start talking about stuff like climate change, you have to learn to read through and look at what's really going on. So I'm going to run you through some test scenarios to see how you evaluate them. Like I said before, it's been a while since some of y'all have been in school, so it would be good to get some practice questioning what science sometimes tries to cram down, oh, I need to fix that. Sometimes tries to cram down our throat, not down our world. So my son comes home, first grade, brings home a little astronomy book, you know, and he's all excited learning about the planets, and, you know, I saw this. The mass of the Earth is 5.7210 times 10 to the 24 kilograms, which is a very big number. That's 6 trillion kilograms, which also breaks down to 13.2 trillion pounds. Now that's a lot of pounds, you know. I mean, if any of you guys have any weight, but the real question is, what is this? Is this an absolute true fact? Is this absolutely made up? Scientists don't know what they're talking about. Or is this an exaggeration, you know? Just to give you an example, a typical pool of water, you know, a pool that you have in your backyard, it's probably like 150,000 pounds of water, you know? Typical house weighs, you know, 2,000 square foot house, from what I looked up with foundation, weighs about 650,000 pounds. And you can imagine that's how much these little things weigh. Imagine how much the whole ocean weighs, or how much Mount Everest weighs, or a mountain range, you know, and try to put those numbers in perspective. You know, is 13.2 trillion, does that seem too much? Not enough? How are they even getting this? Let's do a poll. So everyone take out their devices, and we're going to do a little poll. Oh, I forgot to close out this one. All right, give me 1 second here. Got to see if this technology works up to par. All right, let's turn this poll off, and we're going to do this poll. All right, I don't know if it's going to show up on the screen right away. We shall see. Let's go out of full screen here. Alright, so all you can vote. And this is actually the live response from last class, since I am recording this. So everyone in the class, well, not everyone, only 9 people decided to vote, but hey, voted that your options were yes, of course, scientists know this for sure. No, scientists don't know what they're talking about. Or three, they can't be that certain. This is obviously an educated guess. And this is what most of y'all thought, which makes sense. All right. So now we're going to go to another experiment. Now this experiment is pretty wacky. It's called the cat in the box experiment. And the whole purpose of this is for you to carefully listen to the facts that I'm going to state. And then we're going to ascertain, what may be true and what's not true. So let's start it. So we take a cat. And we're going to take this cat and we're going to place it into a box. This is a very tame cat. Obviously, most of you can imagine placing a cat in a box is no easy task. But this cat will go in a box. So we put the cat in the box and we seal it. All right, this cat is going to be sealed in the box. In this box, there's a little bomb. Now I put the little picture of a bomb. This bomb is not a regular bomb. It's like one of those little micro bombs that they put in Mission Impossible in somebody's head. It's tiny, It's on a completely random timer. All right, so this bomb, as soon as you seal the box, the timer goes off. And the timer is set to randomly pick a time anywhere between the second you seal the box up until 3 days later. So it can go off in the second after you close the box, it can go off an hour, it can go off 12 hours, it can go off 1 day, it can go off 2 days. It's completely random. We have no idea when this little bomb's going to go off. When this little bomb goes off, however, it is going to release a little bit of radiation. Okay, that's kind of anticlimactic. But when this bomb goes off, it's just going to release a little bit of radiation. Nothing big. Here you see there's a little radiation detector. Now, if the radiation detector detects radiation, hence the bomb went off, it will release the lever, which will then drop the hammer, which will then break a glass vial of cyanide gas. Now, this picture, the vial's open, but in reality, the cyanide gas is sealed. Now, if any remember, cyanide gas is what they use in the gas chamber. So, suffice to say, the cat will die. So the bomb doesn't directly kill the cat, but if the bomb goes off, it will release radiation, which will then trigger the radiation thing to drop the hammer to shatter the cyanide gas, and the cat will die. That's how the experiment works. Now, we also have a Geiger counter. Now, if any of you know what a Geiger counter is, that's that thing that measures radiation. You always see it in the movies. It clicks, it goes, if there's a little bit of radiation, there's a little bit of crackle. If there's a lot, then it shoots over, and that means like you're going to die, So the box is sealed. We can't touch the box. We can't see in the box. This cat doesn't make any noise, whether it's dying or it's happy. So the only way we can know what's going on is by using the Geiger counter. The Geiger counter has a simple on and off switch. By default, it's going to be turned off. And so when you turn the Geiger counter on, if you don't measure radiation, then that means the cat's alive, because that means the bomb hasn't gone off, which means the lever hasn't been dropped and the hammer hasn't fallen and the cyanide gas hasn't been opened. If you do measure radiation, that means the cat has died, because the cyanide gas kills the cat instantly. All right? This is all hypothetical, so don't be thinking about all these scenarios where what if the cat does this and that. Like, just run with it, all right? It'll kill the cat instantly. Obviously, if we measure radiation, we don't know how long the cat's been dead. We just know that the cat's dead. Or maybe it died at that instant. We don't know. All right, so you're probably thinking, what do we know? Now, if we put this experiment across the room and we look at it, we could probably think, well, what would we be thinking? What we should be thinking is, what the heck is the experiment? This doesn't sound like an experiment. It sounds like some sick cat torture experiment. Well, this experiment deals with what we know. So, what do we know? Come to our next poll. Let's see here. All right, so here you can vote, and these are your settings. 1, remember, we don't know anything. The Geiger counter is turned off. We haven't made any measurements. We're just staring at the experiment from across the room. Let's say it's been across the room for 10 minutes. I don't know. Let's say we went to lunch. It's been an hour. What do we know? A, the cat is clearly alive. B, the cat is clearly dead. C, we don't have enough information to answer that yet. Or D, the cat is alive and dead at the same time. So obviously we got some jokesters. But go ahead and just take 10 seconds and just think about clearly what the answer is. All right. So we don't know anything, right? I mean, all we know for sure is that the cat is either dead or alive. Until we walk across the room, turn on the Geiger counter, and check to see if the cat is alive or dead, we have no way of knowing the status of the cat, right? I mean, this should have been your top answer, class, because like I explained, completely random timer. We have no idea what's going on until we check, and obviously we have not checked yet. But here's the thing, that's wrong. How is this wrong? The fact of the matter is that scientists claim to know exactly the status of the cat without turning on the Geiger counter. Now this is interesting, since most of us have logically broken this down, and it would seem this isn't the case. All right, sorry, I just had to. Remember, I'm only offering you the truth, people. So what is the truth? The truth is that the unobserved cat is alive and dead at the same time. Now, just think about that for a minute. Does anyone have anything to say about that? Yes, what do you have? You're right. That sounds stupid. You can't have something alive and dead. You're either alive or you're dead. By definition, you're just one or the other. Now, you could maybe be dead and you could be brought back to life, but how can you be alive and dead? Well, let's clarify. According to, oh, dang it. According to scientists, the unobserved cat is simultaneously dead and alive at the same time outside of reality. Okay, just think about what I said. You're the scientist. It's only when you check to see if the cat is alive or dead that it becomes either alive or dead. It is the act of measurement that causes the cat to be alive or dead. All right, so let's break this down. There's a lot of mumbo jumbo in here, it may seem. First, we have introduced the concept of reality, which is a huge question. What do you mean reality? Like, reality is just reality. Now, I'm not talking about if the tree falls in the woods, it doesn't make a sound. I'm not talking about that may be reality for you. We're not talking about psychological reality. I'm talking about reality, is in what's real, what's real, what's real. All right? Now, this question is going to come up, and we're going to tackle it head on through actually ingenious experiments later. But right now, we're just dealing with the concept. Like, what are you talking about? Now, it's only when you check to see if the cat is alive or dead that it becomes either alive or dead. Okay, this is something completely measurable. I say it's the act of measurement that causes the cat to be alive or dead. So it's not just, but so obviously in this experiment, in order for you to check whether the cat's alive or dead, you have to do what? You need to turn on the Geiger counter. Now, the Geiger counter is a measurement device. It measures radiation. What scientists say is that it is the act of measurement. It is the fact that you turned on the Geiger counter and that you took a measurement to check that causes the cat to then become alive or dead. Yes, question. Doesn't make any sense. That's quite true. It doesn't make any sense. First of all, reality. What do you mean reality? And this is what I already said. We're not talking about subjective reality. I mean reality as in reality. As in nothing is actually in the box as soon as we close it, since the living and dead cat are outside of reality. Okay, this sounds even stranger. Now you should be getting frustrated because last time I checked, reality was really reality, just like time, right? I mean, it is what it is. But if you're frustrated, don't worry, it gets better. Let's take our Geiger counter and let's make it Wi-Fi compatible. Now, we're going to reset the experiment. We're going to redo it all over. But this time, you're going to attempt to accept what I just said, which obviously you shouldn't be accepting because if you were rational at all, this should all sound like gibberish. But let's just assume for a second. It's the fact that you turn on the Geiger counter. That the Geiger counter looks, it's the act of measurement. Let's just personify it. That the Geiger counter is now looking with its sensors to see whether there's radiation, which thereby it's looking to see whether the cat's alive or dead. Let's test that out. So we're going to make it Wi-Fi compatible, meaning we're going to use an app on our phone where we can turn it on or off. All right? Now, remember, the app on our phone, all it does is turn it on or off. Doesn't give us a reading, doesn't do anything. It's just an on and an off switch. Now we're going to take this whole experiment and we're going to place it outside because it's hot outside and we want to stay in the AC. And then now we're not looking at the experiment. The experiment is completely outside. It's a brand new cat, it's sealed, everything's been reset. Now we use our phone and we turn on the Geiger counter. So the Geiger counter is observing, so to speak, the cat. So based on what I told you, does the cat collapse into reality or not? Well, your answer should seemingly be yes. I just told you that it's the act of observation. Scientists actually say no. It is not until we go, in this example I said we go outside, but it's summertime, so let's say it is not until we go outside the house and that we look at the Geiger counter and take a reading ourselves that the cat collapses into reality and becomes either dead or alive. So this is what I'm saying. What I'm saying is that it's not merely our observation of the cat that collapses it into reality, but our conscious observation that creates reality. Let me break this down further. Before, we said that it was the act of observation, meaning the Geiger counter observes. I already broke that down. Now I'm telling you, if you turn on the Geiger counter and you're not looking, you don't know what it's on, nothing happens. Cat's still alive and dead. It isn't until you walk over to the experiment and you look down with your own two eyes at the meter and you actually visually see, consciously, that the cat becomes either alive or dead. So now it's not merely saying observation, but it's conscious observation, meaning you are directly involved with the experiment. Consciousness, really? That's psychology, not physics. You're taking us back to medieval times. This is less science and more like science fiction, even though that's technically untrue because science fiction is at least plausible, This doesn't seem plausible at all. So look, we're going to reset the experiment again because as ridiculous as this all is, we're still not done. This time, new cat, new box, everything's fresh, new bomb. But this time, After we're done setting up the experiment, we're going to leave. We're going to go home, get some rest, go to sleep. And you know what? We're not going to come back till 3 days. We're going to wait 3 days and come back. Because remember, the timer's on a 3-day timer. And we're going to come back maybe 3 hours before the timer is definitely going to go off because it's on a 3-day timer. Or you know what? Let's make it more complex. Let's say the timer's on a 7-day timer, all right? And we come back 3 days later, so who knows if it's gone off or not. Now, when we take a measurement, this is important to realize, the cat will not only be dead, but will have developed rigor mortis and will have decayed for 3 days. Conversely, if the cat is found alive, it is also starving and skinny. Now, this seems pretty obvious, but obviously if we find the cat's alive and we decide to open the box, yes, the cat's going to be alive, but the cat's not going to be exactly the same as when we left it. The cat's going to be starving, it's going to be skinny, it's going to be, it's going to be running to get some water. It's not going to look the same. It has gone through some torture in that box. However, if the cat has died, depending on when it died, let's say it died 5 minutes after we closed the box, it's been dead for 3 days. I mean, that thing is cold, it's stiff, maybe there's some type of decay depending on what the conditions are in the box, It's not going to be the same. Okay, well, that's cool, but what am I missing? Well, the moment before you observed the cat, or consciously observed the cat, it was, for a whole 3 days, simultaneously dead and alive, outside of reality. As soon as you made the instantaneous decision, as soon as you looked and made the decision, in the present, so right now, you looked at the Geiger counter and you observed the cat, you created the cat's past history. So what you do in the present changes the past. All right? Oh, well, before we do that. Now, you could be saying, oh, no, that's cheating, that's not really, because, if it was alive, then it was alive the whole time, and it was already getting skinny. If it was dead, it was sort of dead the whole time, and it was getting deader. Or you can think of the cat wasn't just alive and dead at the same time, but the cat was alive and getting skinny and dehydrated and hungry and starving. Or the cat was dead and was dying and going through everything that would say it's dead. Now, outside of reality, so to speak. And as soon as we looked, we didn't really create the past history. We just collapsed into history what was happening. But for the last 3 days, nothing has been happening. They've both been happening at the same time. Maybe neither of them been happening. It's sort of subjective. Yes, what's your question? Exactly. If you're really clever, you should have picked up on the fundamental problem with this entire thing is, how do you know? Like, even if what you said, even if this claim was true, when you open the box, the cat is going to be, no matter what, one thing or another. And when you measure it, you're going to measure one thing or another. So who is anyone to tell you what's going on when you're not looking at it? And that's a very good point, which will be addressed. So here's the real truth. This doesn't work with cats, obviously. This is just a thought experiment. And the purpose of this, you'll understand later why it's set up the way it is. But the truth is that atoms don't exist in reality. They can be here, they can be there, they can be anywhere. I do not like green eggs and ham. I do not like them, Sam, I am. But in reality, they are technically nowhere. They only exist as possibilities to collapse into reality. And it's our conscious observation of them that collapses them into reality. Now hold up, wait a minute. Atoms don't exist in reality unless we observe them? I mean, it doesn't take a genius to deduce the ridiculousness of this argument. So first I need to clarify, what is considered observation of an atom? Now when I look at the wall, I see, let's say I look at I don't know, let's take something easier. Let's say I'm in a metal shed, and I'm looking at the wall, which is a big sheet of aluminum. Now I'm looking at the sheet of aluminum, and I can see the aluminum. If I get really, really close, I can see the imperfections in the aluminum, and I can see the grains and rust, but I can't really see atoms. I can't see that close. So when I say observe an atom, I mean look at it with an electron microscope. Now, most of you should remember, or just know intuitively, atoms are very, very, very small. And With a regular microscope using a light and a lens, it doesn't care how powerful it is. There's no way you can see an atom. It's too small. It's way smaller than anything you can see. You actually have to shoot electrons, which, if you remember, are parts of atoms, little tiny things, part of electricity, which we will talk about in depth. But you have to shoot microscopic things at these atoms just to see them. So that's what I mean when I say observe an atom. So the obvious argument is pretty simple. If the smallest part of larger things can't be real, then how can the larger things possibly be real? Let's take a look at this. So here's a molecule, 3 atoms, 2 hydrogen atoms combined with an oxygen atom. Again, you can't see this unless you have an electron microscope. Any of you have an idea what this is? Yes, H2O, water. So, according to what scientists are saying, this does not exist in reality until you observe it, but you can't observe it unless you're in an electron microscope. So, what does a whole bunch of water molecules look like? The ocean. So you're looking at the ocean, but you're not looking at the atoms. Now, the ocean's real. Obviously, we know the water's real. It has very real properties. We sail on the water, we drink the water, we do everything with the water. But according to what scientists claim, well, when you look close enough, they're not really there until you actually look. Before you looked, they weren't there. This is madness, it would seem. So we're all scientists on board with this, Like, really? I mean, this can't be a universal thing, What did Albert Einstein have to say? I mean, we all trust Albert Einstein, right? I mean, he's Einstein. Even if you don't know who Einstein is, or all you know is E equals mc squared, and you have no idea what that means. I mean, Einstein's it's like a verb, Like, you ain't no Einstein, I mean, you may not even know what Einstein means, but if someone says you ain't no Einstein, it means you're not that smart. But let me tell you, Einstein was the perennial genius of the last century, if not more than 2 centuries. And he really was a super genius. So it would be very interesting to see what Einstein had to say about all this. He said, "I'd like to think that just because I'm not looking at the moon, that it's still there." So Einstein was obviously not on board. He was like, really? I mean, this is ridiculous. This is ridiculous. So how can scientists possibly believe this? I mean, before I got into this, we all had a pretty good understanding what scientists are and what scientists were. They're like the doubting Thomas. I will not see unless I can touch, and I must believe. Quantum theory. Quantum theory is what states all this. Quantum theory, so what is quantum theory? That should be your question. Quantum theory is the foundation of all science, and certainly modern science. It is the most proven and tested theory in all of physics. All of our modern technology is based upon it, meaning your computer technology is based on this. So you cannot believe atoms are real and not real. You cannot believe cats are alive and not dead. And that's fine. But put down your cell phone, put down your computer, and put down anything in your home that has an electronic circuit in it, which is pretty much everything. Because you can't believe in any of those things either, because they're all based off of this principle. Without the quantum theory, we would be stuck in the 20th century with steam power trains and the telegraph. A scientist once remarked that without quantum theory, we'll be in the dark ages. And one of his colleagues immediately said, actually, no. Without quantum theory, we would be stuck in the 20th century. We wouldn't have progressed and moved to where we are now, because lasers are based off quantum theory, and lasers are fundamental in everything, not just of the reading of discs and lasers and CDs and manufacturing. Lasers have so many applications beyond what you can even imagine. So why hasn't anyone heard of it? Now, very few of you probably have even heard of quantum theory, or if you heard of it, you're like, The big thing now is quantum computers, many of you heard of quantum computers. We've all heard of Quantum Leap, the great TV show with Scott Bakula. Although recently I watched a rerun and it was really cheesy. But, and actually it'll be fascinating to really learn what an actual quantum leap is. But for the most part, no one's ever heard of quantum mechanics or quantum physics, which is the same thing. But the word quantum is being used more and more because of what it implies. And we'll go into what it implies later as we go more into depth on what quantum theory is. Why isn't it taught in school? At least mentioned. It was never taught in my class. Now, I found out later that's wrong because I actually busted out with my physics textbook from when I was a sophomore in college. And sure enough, it was in there. Now, we never got to it. We know how your science classes, these books are huge, and they're like 80 chapters. And, in 2 semesters, you only do the first, 70 chapters. You never get to the last portion. Well, it was in that last section. So technically, it was in there, but no one ever covered it. What can science possibly have to hide? That's the real question. Most of us, when we think of science, we're like, they're not trying to hide anything. They publish all the time, telling they cram down what they think they discovered down our throats all the time. So why would they possibly have this to hide when this is the foundation of all science? And it's like, they're not talking about it, Obviously, it's something that you think they would talk about. Well, here's the explanation. It's simple. Quantum mechanical theory and the things it says about our world isn't commonly taught because of its shocking nature. Gee, Sherlock. Quantum theory points out truths about our world that would leave most people questioning science. That's the real hit right there. And that's really what it always comes down to. Is scientists don't want to be questioned. They want to know, look, you guys know exactly what you're doing. If scientists were to start running around saying the stuff that I've just been talking about the past 30 minutes, do you think people would trust scientists? Really? It doesn't matter if they told you it was true or not true. You'd be like, dude, you're off your rocker, So you need to get your act together. And I guess my battery's low. Scientists doesn't like to be questioned, and this is why in the 50s and 60s, it was practically forbidden to speak about quantum theory in a non-orthodox manner. Meaning what? Quantum theory, again, was just mentioned in class, but it wasn't, broken down into its meaning and what principles. You're gonna see as this class progresses how most of this stuff is talked about and not talked about at the same time. Meaning, scientists have a way of saying things that are true, but are completely misleading. Now, when I say quantum theory will shock you, what I really mean is it will shock your basic sense of intuitiveness. What makes sense to your mind? It makes no sense. None of this should make sense, the things I've been saying. This is why universities do not want to teach it, since they don't want lesser minds running away with fantastical notions that they couldn't possibly comprehend. Now, this is a typical elitist attitude, oh yes, we know better. But in a way, they got a point. You can imagine if I were to tell somebody this, right, and not give them a firm foundation, which this class will do, you can come up with all sorts of stuff, like the Matrix. The Matrix is based off these principles where they just took it to a fantastical notion. You have to be really, and I caution you, and I'd say don't do a lot of research until I'm done with this class, as it'll help you do more research on your own. But 90% of books on quantum mechanics, New Age. New Age, crystals, the power of your mind, and they involve no science. They just understand this basic thing, and they just kind of run with it. And we'll cover some of the things that they think and how it's just completely ridiculous it's even more ridiculous than what I'm saying, so to speak. And how they're able to do that, just with, obviously, lack of understanding. Niels Bohr. This guy we're going to be seeing a lot of. He's one of the founders of quantum theory. He's the one that got the whole ball rolling. He's the one that championed it. He was all up in the mix on this stuff. What did he have to say about quantum mechanics? Anyone that is not shocked at the nature of quantum theory has not understood it. So any of you who aren't freaking out, it isn't because you're just so cool. It's because you obviously are not realizing what I'm saying, because you should be shocked. Because what I'm telling you, I'm trying to tell you that this stuff is true, and your brain should be saying this can't be true because it doesn't make any sense on so many levels. So here's the question. How can any self-respecting scientist rationalize this and still claim to be scientific? That was my question. Or a better question would be, what exactly is scientific thinking? Since if these scientists claim to be operating in this manner, I must be missing something, Now, when I heard this, I was like, dude, no scientist could ever believe this, but scientists do believe this. So what am I missing? Apparently, maybe I'm not thinking like a scientist. So let's step back a minute and look at some history to really understand scientific thought. And any history on science, you got to go back to Aristotle. He's the father of ancient science. His work on physics and metaphysics stood unchallenged for nearly 2 millennia and were the de facto standard for all scientific thinkers. This guy was amazing, make no doubt. And do any research on him and see how all of our all of our modern science and the way it's structured and our learning processes all came out of this guy's head. And of course, his Socrates and Plato before him, but he was a great elaborator. However, his greatest strength was also his greatest weakness, and was most likely the reason scientific thought did not progress for millennia. Well, what do you mean? The Greeks were thinkers, meaning they talked and they talked, and when they were done talking, they talked some more, and then they talked. So they were debaters. We all know this. They walked around in their togas, and they talked, and they debated, and they were people of reason, and they had a lot of other issues, but that's kind of one of their strong suits. They thrived on debate. Reason and science was based on these same notions. Science to them had to make sense to the intuitive mind. Whatever your scientific stance, you needed to be able to defend your stance verbally with reason. Reason being that it made sense intuitively to the masses. So you need to, if you want to believe a scientific principle, you have to debate it openly. It needs to make sense to your peers as a whole, not just to a few elect people who are as smart as you think they're as smart as you think you are. They had no notion of experimentation the way we think of it. I mean, even if they did, it wouldn't matter. If it didn't make sense, so to speak, it failed. Experiment or not. Now, the Greeks didn't do experiments or didn't have experimentations the way we think of it, but it's important to note that in their culture and how they derived it with reason and thoughts and logic, that experiments wouldn't matter because experiments don't deal with logic and reasons. Experiments deal to test what is true. And it didn't matter if I were to show them a test that proved this was true, they would say it's a trick or it's a ploy. It doesn't make sense to me. Now the thing about this is this shouldn't be sounding strange to any of you, since this is how most of us work things out as well. Last time I checked, how many times have we said to someone like, dude, come on, think about it logically, or come on, like that doesn't make sense, like let's use our reason, The key difference in this is that we are heavily influenced by not just our intuitive notions, but higher scientific thought. What do I mean by that? Meaning this, the earth is flat. Now most of us would chuckle because we're like, dude, really? People used to believe the earth was flat, That's back in medieval times. They didn't understand the earth was round like we do, right? That's intuitive, like, duh. But my question to you is it? Last time I checked, everything looked pretty flat, especially in Arizona. Imagine going to Iowa, You can get up on the tallest mountain. You can see out as far as you can see. Technically, if you can see out far enough, people say you can start seeing curvature, but that could easily be a trick, But for all intents and purposes, the earth seems flat. There's nothing intuitively logical about the earth being a sphere at all. The earth is spinning at 1,000 miles per hour. Everyone knows the earth spins, like duh, but really? Like, what's intuitive about that? Last time I checked, when you're moving, you can feel it. And if you're moving at a high speed, like in your car, moving at 65 miles per hour and you have your windows rolled down, what's different about that? Not just that things are moving past you quickly, but what do you feel? You feel a wind. You feel a mighty... If the earth was spinning, if you were to say to the Greeks, the earth is spinning at 1,000 miles per hour, they would laugh at you and say that makes no sense. This is why. If the earth was round in a sphere, which is ridiculous, and if it was spinning, we would feel a great and mighty rushing wind. This makes sense. This isn't counterintuitive. This is completely intuitive. The earth is not at the center of the universe. Oh my gosh, really? Those medieval people thought that everything orbited around the earth and that we were the center of the universe. See how cocky people were? I mean, really, But again, I turn it around to you. Last time I checked, all the stars and the planets move over and around us. And they move over and around us pretty regularly. And obviously we're not moving, so it makes sense that if everything's moving around us and you're not moving, you don't feel like you're moving, you're obviously not moving, and everything's moving around you, then it would stand to reason quite simply, and using your common sense, that we are the center of the universe, and that everything is in fact going around us. And last but not least, if you really want to convince someone that the entire Earth, hey, not only is it flat, and it's actually a sphere, and not only is it spinning at 1,000 miles per hour and you don't feel wind, and not only are we not at the center of the universe, but we're moving at 67,000 miles per hour. Now, this is an unimaginable speed just for regular people. The ancient people, it's not even a number that they would even compute. But that's how fast the Earth is moving. Because obviously it takes one whole year to go around the sun, and our orbit is very large. It's millions of miles. So, you got to move pretty fast to get around that. Here's my point, is that there's so many things that we think are logical that actually aren't. We may say duh, there's a magnetic force and blah, 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 but really, what do you really know about magnetism? A piece of metal that emits forces that pull or push? That seems pretty magical to me, Who would believe this? Or would we believe this? If we were the ancient, if someone was telling us this and we were an ancient, we wouldn't believe this. We would use our scientific reason to come up with a logical explanation. We would try to make sense of it. Now, are you starting to see the problem? Galileo. Most of you have heard of him. Born in 1564, he would revolutionize and basically start the rebirth of science. He was a fully convinced Copernican, a view which almost got him killed. Copernicus, as you remember, was the first one in Europe to formulate that, the Earth's not the center of everything. Actually, I think we're all going around the sun. And of course, he was smart enough to publish his findings right before he died. Galileo was not so fortunate, and he actually confessed, this makes sense. And it almost got him killed by the church. And so he was under house arrest for most of his life. His controversial views withstanding, most of his thoughts came in direct conflict with Aristotle's views, most notably Aristotle's view on motion. Now, when you roll a ball across the floor, it will eventually come to rest due to its desire to rest. This is what Aristotle believed, and this is what he taught. This is what everyone believed. Now, if you take a ball and roll it across your carpet, it'll eventually stop. Obviously, it doesn't stop because it has a desire. Inanimate objects don't have desires. But Aristotle's like, no, everything wants to stop. It doesn't want to keep moving. Galileo said it was friction that caused an object to stop. So before I read the next sentence, that he also broke down what friction was, and he would say, no, it's actually the carpet that's pushing against the ball, and that's what is hindering the motion of the ball, and that's what's causing it to stop. If you roll a ball on smooth tile or ice, it's going to go a lot further before it eventually stops. But eventually it will stop because there's still friction. There's just less of it. He also asserted, in the absence of air resistance, heavy objects and light objects will fall at the same rate. Now, as soon as he said this, his contemporaries laughed at him because they were smart, and they're like, okay, that's ridiculous. Galileo would say, why is that ridiculous? Well, if what you're saying is true, then you could drop a bowling ball and a feather, and they would hit the ground at the same time. Now, air resistance or not, that's ludicrous. That's stupid. Of course, we now know, or at least we should know, that this is true. In a vacuum, meaning if you put it in a chamber or a room and you suck out all the air, a feather and a bowling ball will fall at the same rate. And to put it more simply, anything, a caterpillar, a car will fall at the same rate as a feather. And there you saw it, a ball bearing, which is obviously very, very heavy, and a feather falling at the same rate. So despite what we may think, all objects will fall at the same rate, regardless of weight, when air resistance is neglected. So all that stuff you learned as a child watching Wile E. Coyote, not true. Here's another classic example of science interfering with our common sense. Again, everyone's fallen for it. I mean, you don't have to watch Jay Leno, and I actually tried to find the clip, but if you ask 9 out of 10 people will get the question wrong. Okay, it depends. On the street, 9 out of 10 people will get the question wrong. What falls faster, a ton of feathers or a ton of bricks? And that one, of course, is even more obvious because, a ton is a ton. But the notion is that it doesn't matter what's what, feathers fall slower because we all know feathers do fall slower because of air resistance. But if you ask me, yes, I get it. The wind is going to push up more against the feather, but at the end of the day, the feather is lighter. It's lighter. It can't fall at the same rate as a giant bowling ball or a car or a house. Ask any unlearned child if a feather and bowling ball can fall at the same speed, and they'll say no. Why? Because it's common sense. To prove his point, he contrived a revolutionary idea, the experiment. Galileo was the first to really formulate what we know as an experiment and the process and procedures that were entailed with doing an experiment. Now, this sounds ridiculous to us since experimentation is so fundamental. Again, this is taught to us. It seems common sense, it seems intuitively to do an experiment, but why? We're taught it over and over. We do our science fair, we do our hypothesis, we do everything. Like, we understand innately from the youngest age what experimentation is and how it's necessary. But by all means, experimentation, the act of doing an experiment is not intuitive. So in his famous ball dropping experiment, he dropped 2 balls from the top of the Leaning Tower of Pisa. Both spheres were the same size and dimensions. However, one was made of a light wood and the other was made of lead. So here he took 2 balls. You can imagine 2 spheres. Let's say large spheres, like the size of a shot put, all right? One of them made of solid lead, like a shot put, something very heavy. The other one, the same exact size and roundness and smoothness, but it was made out of a very light wood. And not just that, but it was a hollow wood. So it was really just a shell, as light as you can make it, but still hard. Now, as you can imagine with wind resistance, if you remember anything in science class, that, spheres have very, very good wind resistance and they just wrap right around them. But since they're the same size and same dimensions, they're going to have equal wind resistance, which will basically give it the same conditions as a vacuum. Since they both are equally hindered by the wind, then you can now rule wind and air as a factor. Over and over he dropped the pairs of spheres to the spectators below, and over the crowd saw and heard the spheres hit the ground with their respective clanks hitting in unison. So what he did also is he made it so the metal, the ball of lead hit a piece of metal, a metal board, so to speak, below, and that the wood hit a light wooden plank. So not only could you visually see the balls falling together at the same rate, you could see them hit the ground at the same time, but you can auditorily hear both their respective clanks. You can imagine the sound of a light piece of wood hitting a piece of wood really loud, and the sound of a piece of metal hitting a piece of metal, two very different auditory sounds. And you can imagine hearing them in sync, in unison. So it was like a 1-2 punch where you can see both at the same time. There's my example right there. The results were astoundingly clear. So did his colleagues rejoice and pat him on the back? I mean, you think at this point it was like, oh my gosh, Galileo, you are the man. I mean, you just broke it down. Like, I apologize, for telling you were an idiot earlier because clearly, maybe it doesn't make sense, but, it seems to make sense to me. Absolutely not. They said this was just a contrived situation. It is flawed since it does not make sense. Now, before we get to this last paragraph, let me harp on that a little bit longer. They saw what happened. They saw the results. But the power and the fact that they saw the results did not overshadow the fact that they knew that it didn't make sense to them. So since it didn't make sense, the flaw was in the experiment. Like, no, I don't know what you just showed us, but it's a trick. Or maybe you're showing some other principle that will make sense to us. But this, what you're saying, still doesn't make sense. This is when Galileo took it to a whole new level. He furthered scientific thought by remarking, he said science should only deal with those matters that can be demonstrated. Intuition and authority have no standing in science. The only criterion for judgment in science is experimental demonstration. And Here's an artist rendering. Now, wow. Let's think for a moment. Galileo not only challenged the authorities at the time, meaning the church and his contemporaries and other scientists, but he took science back to base zero, meaning what? If you want to say something is true in science, prove it experimentally, period. Now, he went on to clarify what experiments were and how they needed to be repeatable and probable to reasonable individuals, but you can see how he pushed the reset button on thinking. Because up until this time, science was a mixture of mysticism and alchemy and quasi-religious beliefs, and people just, if they couldn't make sense of something, it was the angels or something else. Galileo's like, no. The only thing that's true in science is what you can prove scientifically. Remember, they had experiments to prove the Earth was flat. Sailors said, hey, I'm going to go out and see how far this ocean goes. And they never came back, so they must have fallen off, right? After all, the Earth looks flat from my perspective. Well, a reasonable person would concede that this is less of an experiment and more like an assumption. And we all know what happens when we assume. So how does all this history help me? I just covered it. You're probably thinking, okay, what does this have to do with what I said about cats and atoms? Okay, I have to admit I did trick you a bit, or more like I misled you. I kept saying quantum theory, not because this is the incorrect word, but because I knew it would invoke a false emotion. What do I mean by that? The atom being real and not real is what we observe in nature, just like the feather and ball bearing falling at the same rate in a vacuum is observed in nature. Quantum theory only attempts, and it does so extremely successfully, to make sense of what we observe in nature. So in essence, by you laughing at this video, or, and thinking like this is ridiculous, you are actually equivalent to the dudes that were laughing at Galileo when he dropped the balls. This actually occurs in nature. We can see how atoms are not real until we observe them. And we can see how the cat can most likely be alive and dead. Quantum theory is what we use to explain it. Because, like all scientists, we try to explain mathematically what we can see around us. But we're not making that up. It's not like evolutionary theory where we're extrapolating and hoping something is true. This is what we see now. This is what we see in the present. Gravity is a theory used to describe what we see when we drop things. Does anyone not believe gravity is real? A theory simply describes mathematically what we experience in the real world. It does this according to the scientific method, and that it provides a well-substantiated explanation of gravity that produces consistent and repeatable results. So, again, a scientific theory is a well-substantiated explanation of some aspect of the natural world that is acquired through the scientific method and repeatedly confirmed through observation and experimentation. So it's not even that you experimented it, but you have to be able to repeat it over and over and over. It has to be something that is true all the time, not just some of the time. So what am I saying? No one questions these types of theories. No one's questioning Newton's laws of physics. He has all these great equations to figure out. When you launch a projectile, a catapult ball, you can calculate exactly where it's going to fall. We use Newton's laws for everything. Like, you'd hope calculus is true and Newton's laws are true. Otherwise, you wouldn't trust the buildings you're in. You wouldn't trust the fact that we can send rockets to the moon or launch satellites. That's all just physics. It's all just laws, It's all mathematics used to describe what we see in the real world. However, quantum theory does the same thing. It simply attempts to model what we see in the real world, and it does so with a well-substantiated explanations, and it provides consistent and repeatable results. So it does both of these things. Next, not all branches of scientific theories are created equal. What do I mean by that? Well, you got physics, chemistry, biology. I put psychology at the top, but every other branch of science is on top of the biology, whatever. Biology, chemistry, and physics, they're generally what's called the base sciences. They're the base scientists because they're the foundation of everything. So let's take, for example, psychologists, right? And let's say you have whatever, you're depressed. You suffer from depression. Psychologist has, they have their own scientific methods of diagnosing things, and they understand, the way you're thinking, and you can talk to them, and they have a clear um, scientific understanding of how the mind works and how behaviors work. Now, I say scientific is because, you know, there's an order to things. They publish journals, they do things, they do tests and run things. I mean, psychology just gets a bad rep. Most people don't like to think of psychology as a science, but I just use it in this example because the next step is biology. Now, the psychologists, if you're suffering from depression, what do? They subscribe you medication, and that kind of blurs into chemistry. But the biology part is they understand that the brain is where your emotions are centered. And the brain biologically is composed of nerve cells and nerve synapses and electrical signals and all this stuff. But in biology, the complexity is very high, obviously, because you're dealing with mechanisms and we still don't fully understand the brain. We understand like the pieces of how it works, but not as it works as a whole. But it's our chemistry and our body, our biology is extremely complex. So any things that usually in the biology sphere you come up with are still subject to a lot of interpretations. Like we know the appendix, so the appendix doesn't do anything. And then we've realized, okay, the appendix does do something. The biologist obviously goes into detail about what the appendix does and how it does it and how it produces proteins, white blood cells, whatever. But the biologist looks at the big picture and then extrapolates like, oh, well, when we were monkeys, we used to have a tailbone and that made us need an appendix. Now I'm reaching there, but you can see how they have to branch out a lot further. Chemists have to branch out a lot less because they deal with the details. They're dealing with, okay, well, as far as the brain's concerned, neural synapses and the firing and, people don't realize like when you have horrible back pain and you take a muscle relaxer or a pain to, the doctor gave me some pill when I threw out my back, and I forgot what it was, but I looked it up and looked at all the side effects, but I realized what it was doing. Here's a chemical compound, molecules, done in the lab, that you take, it absorbs in your stomach, goes into your bloodstream, and finds its way up to your brain, and then tricks your brain, and blocking the signals that tell your body it's in pain. And that's pretty remarkable that they're able to do this through chemistry. And chemistry, again, kind of has it's kind of a middle, it gets a bad rap, when you watch the commercials and we're like, oh, the side effects are, heart attack, death, all these crazy things, suicide. But at the same time, when we're sick and we go to the doctor, we're like, dude, okay, give me some drugs. Like we can easily chemistry, but for the most part, we all understand that the body is immensely complex. Even if they were to take you and just do $1 billion worth of tests on you and create a drug that works perfectly for you that has no side effects because it's tailored exactly to your anatomy, your physiology, and your DNA, it wouldn't work on anyone else. Anyone else would have a bunch of side effects. So you can see chemistry has to deal with the high complexity of things. And then, of course, there's physics. Physics in its most general sense deals with the stuff in the natural world. If any of you remember or took physics, but velocities and accelerations and doing all that stuff in optics and it goes heavily and goes into engineering, but as far as it relates here, it deals with the atom and the structure of the atom and how the atom forms molecules and amino acids and proteins. And it's obviously to say that in physics, a theory is pretty solid. They're so solid that for the most part we call them laws. They're called Newton's laws, not Newton's theory. The laws of thermodynamics, not the theories of thermodynamics. Though in reality, they're all theories. There's no such thing as a law in science. We call it a law out of respect when it's worked perfectly for 400 plus years, but for the most part, they're all theories. And here's Albert Einstein again. He said, I've spent more time reflecting on quantum theory than I have on relativity. And this is amazing because remember before I showed you that quote about the moon. And this is when you're going to realize in this class, Einstein has a huge part to play. When Einstein actually is one of the founders of quantum theory. And the ironic part is he gave birth to it, so to speak, and helped cultivate it. And then he got busy working on his theory of general relativity. As you know, originally it was this theory of special relativity. And once he realized there was issues with his theory of special relativity, he went to work for almost a decade, refining and perfecting his theory of general relativity, which was another one of his crowning triumphs. And in the meantime, he saw quantum theory progressed on its own without him. And when he got back to it, that's when he realized that they were saying ridiculous things. And Einstein became the biggest opponent of quantum theory. And he came up with powerful arguments, which, again, may scare some of you, because if Einstein, the perennial genius of the last 2 centuries, made it his mission to disprove quantum theory, and as you can imagine, obviously he failed, what makes you think you're going to do any better? If you think everything I'm saying is idiotic, I might as well reply to you, look, you ain't no Einstein. Example, quantum computers. Now, as many of you know me for a lot of things, whether I do video editing or maybe you don't know me and you're watching this video, but my first thing has been computers and computer programming. I recently graduated from ASU with my bachelor's in computer science, and so computers are my thing. And quantum computers is the whole reason why I'm even teaching this class, because quantum physics has nothing to do with anything with computers. Well, not counting quantum computers, but quantum mechanics. The whole reason why I got into this is because I'm one of those people, if something doesn't make sense to me, I have to figure it out. I'm like a chihuahua on someone's ankle. I will bite onto it, and I just need to learn. I need to have it understand and make sense to me. And when I was taught by my very first semester, my first professor talked about quantum computers, and this is when they were way before they were being realized and worked on. After he was done explaining to me, I was blown away. I was completely blown away. I had my cat alive and dead moment. The funny thing was, no one else seemed to have that moment. I don't know if they just weren't concerned, or maybe they didn't understand the implications. And you'll understand what I'm talking about in a second, but this is how I got started. So, a lot of you, if you're watching this video, you may be wondering, like, okay, well, give me an example. If you say this is true, prove it to me. But the funny thing about that, if you think about it, is it really doesn't matter if I prove it to you, which, again, I will. But the concepts, the challenge to the intuitive mind that God has given us is so severe at first, and that's why I keep talking about it, because the more you think about it and absorb it, the less it's, at least you can get over the shock period and we can really start breaking it down. But I'm going to give you a very real and obvious example, and you'll see, even after understanding the example, it's not going to make you feel any better. And that's basically what I just said. So, first of all, what is a computer? I mean, most people don't even know what a computer is. And I'm going to tell you, really simply. A computer is a light switch. That's all it is. On and off. That's all a computer is. A computer is a billion light switches flipping on and off in an organized fashion. Now, we call them transistors, but it's an on and off switch. On, electricity flows to your light. Off, electricity doesn't flow. Same thing with a computer. Zeros and ones. On and off is all a computer understands, or 1 and 0. And most of you know computers only understand binary. But that's what binary is. 1 means electricity is going to flow in this switch. 0 means it's not going to flow. It's off. The ones and zeros, or binary numbers, are all the computer knows or understands. Again, we know this, but I'm just clarifying on and off. Let's take simple counting. A computer can't count to 10. It can only count to 1, because all it knows is 0 and 1. So how does a computer count? Well, let's take a 2-bit number like 00. So you take 00, that means 0. 01 is a 1. Now, you can technically remove those back zeros since they don't do anything. 'Cause you could put a billion zeros in front of that 1, and it would still be 1, because the 1 there represents 1. Now you move the 1 over a space, and now you have 2. And you fill in the 1 next, you have 3. So if I were to give you a 0 and a 1 and said, give me every combination you can make with these 2 digits, you would only come up with 4. You'd come up with these 4. So this is the ordered fashion. Now let's go a little further. Again, you could put a pair of zeros in front. doesn't do anything. But now you can count higher because you can move the one place over to the left. So now you count to 4, and then put a 1, 5, 1, 1, 0, 6, 1, 1, 1, 7. So with 3 bits, you can count all the way to 8 in this fashion. Now, sorry, 3 bits represents 8 numbers, not count to 8, because 7 and 0 is a number. You have 8. And here it is again. You can take that whole row, put a 1 in front of it, and you can count to 8, 9, 10, 11, 12, 13, 14, 15. So a 4-bit number has 16 combinations. So what's an easy way to find out how many combinations a number has? Oh, here it is again, in case counting to 64-bit is 7 bits. It's 2 to the power of n, n being the number of bits. So if you have 3 bits, I showed you that there's 8 combinations, and again, you do 2 cubed, you get 8. Here in the full picture, you'll see 4 bits has 16 combinations, 15 plus the 0. 2 to the 4th equals 16. All right, so encryption. How many of you heard of encryption? Most of you have heard of encryption. This is what we use to protect all our data and whatnot. Or AES encryption. Generally, government-grade encryption is rated at 128 or 256 bits. So that's why I told you about that. So now, encryption is much more complex than this, so we're going to break down a simple example. Let's say encryption was just like a form of saying your password. And 256-bit encryption is just saying, hey, you know what? You have a 256-bit password that you have to guess. Okay, well, how many combinations is that? Well, 2 to the 256, if we do the math, that's 1.15 times 10 to the 77th. That's 1.15 trillion, 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 trillion combinations. That's a lot of combinations. Meaning, if you were to intercept a government encrypted file, that's how many combinations you got to go through before you break into it. But that's a lot of combinations. But computers are really fast, right? I mean, one thing we know about computers is that they're really fast. Well, how fast are they? And just so you know, and I mention is, when you say a computer is 2 gigahertz, what you're really saying is that the light switch, you know, the light switch, your clock rate, basically every computer starts with just one light switch, on and off, or transistor. I'll just say light switch. And from that controls other light switches, and that controls other light switches. And it's a cascading effect, where before you know it, one switch is controlling the actions of billions of switches, where each switch can only do one thing at a time. But they're all controlled by the one switch, which is like the clock. 2 gigahertz means you're flipping that switch on and off 2 billion times a second, because a giga is a billion, so a gigabyte is a billion bytes. But that's what that means. But let's put that in terms of speed. A top-of-the-line quad-core i7 has 731 million on and off switches, transistors, and they could perform at 153 gigaflops. Okay, so what the heck is a gigaflop? Now, unless you're a super geek, you probably haven't heard the term gigaflops or megaflops. You mostly hear gigabytes or megabytes. A flop is a floating point operation. What does that mean? Quite simply, it means this is when a computer adds or subtracts 2 real numbers. Now, when I say real numbers, I mean a decimal number. Sorry. So 2.1 is a real number. 2 is a whole number. So if you take 2.1 plus 2.1, you get what? 4.2. That is a flop. It's a floating point operation. Remember, computers can only add and subtract. They can't multiply or divide. Why multiply? 5 times 5 is 5 plus 5 plus 5 plus 5 plus 5. You know, if you do everything really fast, you know, you don't need to do the other stuff. That, and it's very, 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 very difficult to do that. But that being said, so 153 gigaflops, meaning a top-of-the-line Intel processor that you can buy consumer grade, does 153 billion calculations per second. So it can add 2 numbers together 153 billion times. So which is why computers, you know, when they do math, even on your dinky little, even on a dollar store calculator, it's like instantaneous, it feels like, you know. Obviously computers, everything they do seems instantaneous. It's just they do it very fast. Graphics cards are even faster. Now, if any of you are into gaming and you have a decent graphics card, these things can have 4,000 cores. Now, again, most of you don't know about cores. You don't even know what a core is. You just know, hey, I have a dual core. Ooh, I have a quad core. Quad is 4. 4 is obviously better than 2. So my quad core is better than your dual core, you know. Basically, to put it in a nutshell, CPUs got faster and faster and faster, all the way till we got to these 4 gigahertz Pentium 4. And then the thing we realized is that they just got too hot. They use up too much heat. And so the smaller and smaller you get these things, you can lessen the heat and you can lessen the amount of energy they take up. So the direction they started to take is, instead of making a really, really hot, powered, takes a lot of energy, 4 gigahertz processor, let's split into 2, because 2 is better than 1, right? Not necessarily, but it works great for marketing. So now you have 2 gigahertz, instead of 1 4 gigahertz. Computer speed is measured in gigaflops. Here's the top of the line Mac Pro. Now I put the Mac Pro, but this is the top of the line computer. So if you were to spend $3,000 plus on a computer system, got it all souped up, well, the Mac Pro is, no, this computer I'm talking about would even be more than $3,000. But if you want to buy a low end, you spend about $3,000, you're looking at about 500 gigaflops. So 500 billion calculations per second. Just put it that way. What about supercomputers? Obviously, the government and people use things like supercomputers. Well, so supercomputers, all they do is scale the operation. So they started something like this. It's called a compute chip. Now, as many of you know or don't know, Intel has a quad core, but they also have a 6-core processor. And when you start getting into servers and high-end, they have a 12-core Intel Xeon. AMD has a 16-core, top-of-the-line server processor. And remember, these cores are not the same as graphics processors. Those graphics cores, yeah, there's 4,000 of them, but they're very, very, very immature. They can't do the type of mathematical, powerful things that an Intel or AMD core can do. But that's why there's 4,000 of them. So, I gave an example of graphics cards, but I don't want you to think of them like, oh, a 4,000 core graphics card, which is about $1,000, is 4,000 times more powerful than one of these 16-core CPUs, because that's absolutely not the case. But that's a whole different computing. So let's just not think about that right now. So on this compute chip, there's 2 of these CPUs. So there's 16 cores each. So just on this little chip, you have a little mini computer that has 32 cores. 2 of these compute chips are what's called a compute card. And you can see next to the compute chip, it has all its dedicated RAM and everything. And so really on this little board, you have 2 compute chips, which means 4 processors. So now you're looking at 64 cores. This is a lot of power. Remember, this is raw, high-end cores. Then you have a node card. You put 16 of these chips or whatever inside this node card, and you do the math, multiply it out, and you get 1,024 cores. This right here is a freaking supercomputer, at least the way I would think of it. Like, that's a lot of power. But it doesn't stop there. You have a cabinet. You pack in 32 node cards into this baby, And now you got 32,768 cores. That is extremely powerful supercomputer. But they don't stop there. These things build and they scale. You can have up to 200, let's say 200 cabinets. That's 6.5 million cores. Just to show you an example, here's, this was number 1. America was number 1 with this computer. It's an open source, like science supercomputer that scientists had access to. But China beat us, so we're now not number 1. But you see it's 200 cabinets. They're all liquid cooled. It's really nice looking. 18,688 nodes. It uses the AMD 16 core, plus they use the NVIDIA graphics card. So they use a little bit of both. There's a close-up. So this is a ranking of the top 500 supercomputers in the world. So I want you to take a look at this for several reasons, and this will all tie together if you just stay with me. On the far left is the rank. So this is the 500th most powerful supercomputer, so the lowest on the list. You see the make, who made it. You see the country. You see the year. This is the number of cores. So this number 499 China has 23,000 cores. Now this is the gigaflops. But if you look, that is a decimal, that's a comma. So this is 133,000 gigaflops. Now I'm sure if you remember, 1,000 gigabytes is a terabyte. So this is actually 133 teraflops. A tera is a trillion. So when you have a terabyte hard drive, you have 1 trillion bytes of information. It's actually a little bit more when you do the math. And in case you're wondering, because we talked about bits earlier, there's 8 bits in a byte. So a byte is 8 bits. Why it's broken down to 8 has to do with computers and how they originally built and so on and so forth. So 1 terabyte hard drive is actually 8 trillion bits. So here we're looking at 133 trillion calculations per second. That's a lot. But let's go ahead and watch the video. And what I want you to pay close attention to is the countries. You see there's a lot of United States, a lot of China. And then the cores, don't really pay attention to that because as you imagine, you see some have a lot less cores than others, but they get a lot more. It's all about how you design and engineer them. If you look at the gigaflops, you see them slowly going up. You know, we're almost to 200 teraflops, and we're already halfway through the list. A lot of United States, Germany, lots of Japan in there, lots of China. Now we're in the top 100. We're at 500 teraflops, and it's going to go up really quick. All the way, we're at, look at that. 1, 2, 3. Number 6 is at 6.2. Now this is a whole different number. Most of you never have to experience anything more than a teraflop. But if you were to do 1,000 terabytes, if you had 1,000 terabyte hard drives, you would have what's called a petabyte, which I know that sounds really dirty. But that's the next thing up in the metric system, is a petabyte. So you see the number, that computer I showed you, the Titan, is at 17.5 or almost 17.6 petabytes. And the Sequoia is right behind it. But the new Chinese one, of course, they always got to outdo everybody, is 33.8 petabytes. So a petabyte is 1,000 trillion. So 33.8 thousand trillion calculations per second, or what comes after trillion in shorthand is quadrillion. That's a lot of calculations. I mean, now the question is, what are these used for? These are all used for mostly nuclear simulations. We don't need to do nuclear tests anymore because computers can do it for us. They're powerful enough to recreate all these scenarios. They have a lot in Japan and Asia with earthquakes, with Europe. I mean, there's so many computationally advanced stuff they do, even with pharmacology. But here's my point in showing you all this, is that if you take the power of every supercomputers in the world, which is basically the majority of the good, strong, working ones, you have 274 petaflops. All right, that's 274 quadrillion calculations per second. Or it's 274,000 trillion. That's a lot of power. But to see where I'm going, we need to take it a step further. What if you took everything in the world, all the computers combined in the world? You took every computer in the world and combined them together. So I'm talking about every computer, every laptop, every desktop, every iMac, every phone. Our cell phones are very powerful machines now. You took every single iPhone, every single Galaxy, and we connected them all. This is how much power we have. And this is, of course, an estimate, but it's a pretty good estimate. 6.4 exaflops. So if you're wondering what comes after petabyte, it's exabyte. 1 exabyte of data is what they estimate the world uses every day. So an exabyte is 1 million terabytes. So it's 1 million trillion. So the whole planet can do 6.4 million trillion calculations per second. That's a lot. Now, let my point emerge finally. Let's say an alien came, all right, and they gave us a 256 RSA encrypted file, and they said, you have whatever, 1 year to decode this. If you don't decode this, we're going to blow up the Earth. All right, so if aliens told us that, this is the only way we'd all get together and hook up every computer in the world to see if we can break into this encrypted file. So we do. And now we have 6.5 million trillion calculations per second, and we're going to focus all that power on cracking this code. Well, here's the math. If you do the math, if you take that 2 to the 200, if you take that RSA encrypted file and you guess using a computer, it would take you 6 or 5.7, but pretty much 6 trillion years to crack an RSA 256-bit encrypted code. That's how many combinations there are. Now, I can't help myself, but I must mention that that's with a government-grade password in your RSA file, meaning it's probably going to be 15 characters alphanumeric. Passwords are very easy to break, even if you use 256-bit encryption, because people do lame passwords, and they put their birthdays, and they put their last name, and they put just people change your password. You know, I just told you how strong computers are. If your password is 8 to 10 characters, most of you complain if it's 8 characters, but if it's 10 and you're thinking like, oh my gosh, this is strong, we're talking a 10-character good password. You know, uppercase, lowercase, you got numbers, you got pound signs. I'm not talking a supercomputer, like a $3,000 powerful gaming machine with like 2 of those 4,000 core processors can break your password in a matter of hours. So, you know, if I've taught you anything through this, change your password, make it stronger. 1 second. Here's my point. My teacher basically broke this all down. Of course, he used the example, the Star Trek example of a Borg cube. And every computer in the world, like making like a Borg cube, like a supercomputer. And this is what I imagine. I imagine this awesome power. Just like that's why I took the time to explain all this, is I want you to imagine the awesome power. But now you realize that awesome power is nothing against this encrypted file, because you don't realize the awesome power of 2 to the 256 power. It's an impossibly large number. Well, here's the revelation. A quantum computer can do this in 1 minute. Just let that sink in. Here I was having my epiphany moment. Like, what? Now I explained to you how computers are fast, and everybody knows computer chips get faster slowly as time goes on. They get incrementally faster according to Moore's law. And then I told you, hey, if you really want to make a powerful computer, it's not that you go to some other company that's besides Intel. It's not like there's another company that makes like a super chip. No, you just take the consumer grade chips and you multiply them, you know, and you make really expensive million dollar machines. But it's multiplicative. You're taking the same thing over and over. And then I explained to you how if you take everything in the world, you have this a massive power. And now I'm telling you, one quantum computer, you can't just kill all that. I mean, we're talking like, okay, let's say the world computer took a trillion years, and a quantum computer could do it in 1 trillion years. Okay, so you cut down on a trillion years. No, a quantum computer can do it in 1 minute. Now you can imagine the implications of this. This is why there literally is a billion-dollar race between us and China, which is why I was having you pay attention to that. Not just China, the whole world. Because whoever achieves a working quantum computer, now there's companies that claim to be a working quantum computer, but not of this type, you know. They're not really a real quantum computer, and we'll talk about that later. But as soon as you achieve this, you can imagine all encryption is broken. You can reveal all secrets. If you pay attention to the news, China's been breaking into our systems left and right, and they've been downloading tons of top secret files. Now, all these files are encrypted. So right now, as you can imagine, the files mean nothing to them, because it would take them a trillion years if they built the most powerful, if they built a computer the size of the whole planet. But as soon as they achieve this feat, and they're able to build a quantum computer, they literally are sitting on a treasure chest that they just can't open, and they're just waiting for the key to unlock it. That's pretty profound. And of course, as soon as you get a quantum computer, they've already theoretically, and they're already working out the mathematics, but you can do what's called quantum encryption. And then you're good again. But then anyone that doesn't have quantum encryption is just screwed. All your secrets are laid bare. The quantum computer will become the de facto standard. And anything below it, it'll be a joke. But here's my point. A quantum computer, a regular computer understands bits, right? I already broke that down, zeros and ones. A quantum computer uses quantum bits, or qubits. I always thought it was qubits, but turns out it's qubits. just like the biblical measurement that we use for the arc. A bit has two states, went over this already, either a 0 or a 1. Now a quantum computer has three states. Sorry, a quantum bit or qubit has three states, not just two. It can be either a 0 or a 1, or, if you can guess, a 0 and 1 at the same time. Here it is again. Alive and dead, real and not real. How can something be on and off at the same time? Or if you look at it logically, because 1 is true, 0 is false, how can something be true and false at the same time? It's not making any sense. But think about it this way. Now that you know the computers, how fast they are, and I told you that they only seem to go so fast because they do things so many times a second. But you must realize that they only do one thing at a time. So if you took all those 256 zeros and lined them up, and you watched them tick off like a counter, and imagine a counter moving so fast, where probably like the digits move so fast they didn't even seem to, they probably seemed stuck at a 0 or something, because they flickered between 0 and 1 so fast. And you slowly saw that 1 move, and all these other numbers move impossibly fast. That's because the computer can only do one thing at a time. But a quantum computer has this third state, which is really what it uses. So now imagine those 256 zeros and ones all lined up on a screen, and that they're flicking impossibly fast between 0 and 1, where they basically look like this picture here. They're 0 and 1 at the same time. Oh, well, I should have finished this slide. A classical computer has to go through one state at a time. One state at a time. A computer, what? I need to fix that slide. A quantum computer's qubits are in all possible states simultaneously. Every possible combination exists because every 0 and 1 is a 0 and 1 at the same time. But this is happening outside of reality. It is simply the goal of the quantum computer to merely select the correct answer, subset by subset. So this is the way you need to imagine it. Imagine if you can look outside of reality into this infinite out. The quantum computer, since it's a 0 and 1 at the same time, sees every combination, sees all trillion combinations at the same time. How, why, it's really not for you to really wrap your head around, because we still can't wrap our head around the cat or the atom. But this is what it is. And by selecting it, it's kind of looking like, oh, it's over here, and I'm going to group it down over here, and it's generally over here. Now again, that shouldn't make much sense, but again, I'm not going to teach a class on quantum computational theory. Regardless, this is the truth, and this is how it works. And as you can tell, I gave you a real example. I mean, Google is using a quantum computer right now. It's one of the ones that physicists say isn't fully proven to be a quantum computer because they haven't let physicists analyze it. But who cares? Google's using one. I think Intel bought one. They're like $20 million. And they're only good for certain stuff. They don't work for encryption yet because there's a lot of reasons, but they haven't quite got there yet because it's a very weak computer. And before we get to this quote, I just must add, knowing that example, even if you could barely understand it, it still shouldn't take away the feeling in your stomach where this is completely bizarre. And I go to this Einstein quote because, again, Einstein was the biggest opponent of all this. And it's funny because when you really understand his crowning, his major argument against it, which seems solid, actually. When I first read it, I was like, dude, Einstein nailed it. Like, he finally put the nail in the coffin. But he instead ended up proving even crazier aspects of quantum mechanics. If you can believe it or not, the whole alive and dead conscious observation, that's just the tip of the iceberg. I don't even want to reveal the other stuff because it's just, your brain can only handle so much, But this quote is really powerful because a lot of people misunderstand it, and it has really deep implications. Einstein says, "Subtle is the Lord, but malicious he is not." Einstein was like, look, I see your experiments. I'm not doubting quantum mechanics. Hello, I gave birth to it. I'm Einstein, okay? I understand it. I'm Einstein. But obviously the conclusions you're coming to they make no sense because obviously you're missing something. And this happens in science all the time where you develop something and it's not complete. Like you understand one aspect and you wait for someone else to kind of jump onto another aspect. You're going to really understand that in class 3 when we start breaking down the history and breaking down magnetism and electricity, how they slowly pieced it together. Einstein's like, look, God is subtle, you know? Subtle is the Lord, you know? It's not always there in front of you. As soon as you see it, it's deceptively simple and it's beautiful, you know? And the equations are elegant, you know? The universe really truly is elegant. But the God is subtle, but malicious. Remember, malicious isn't just like mean. Malicious is a very strong, powerful, negative word where you're talking about someone just doesn't do you wrong. Like they try to do you wrong. They purposely do you wrong. They plan to do you wrong. Einstein saw this, his heart and his passion, and with a lot of scientists, isn't so much that quantum theory is ridiculous and obviously you're missing something, but they took it personally because they're like, no, I mean, scientists may not believe in God, but they do in a sense. A lot of these scientists see science as God. And to say in the end that you just don't know and stuff is there but not there and alive and dead, that doesn't sit comfortably with them, you know? And Einstein actually personified it in saying that, you know what? God is subtle. You're missing something, but malicious. He's not cruel. He's not mean. He would not do that to man. He would not give man a mind to look as far forward as we have, only to snatch it away at the last minute. And this is actually a core thing we go into, I hope to break down later, with sort of like the Tower of Babel. One of the things I always found funny about the Tower of Babel, not funny, but you know, not like I doubted the story. I am a Christian that believes the Bible literally. But one of the things that always just didn't make sense to me is, here you have man, right? And they're so smart, and they were on top of it, and they were building a tower to the heavens, and they were beyond what we were capable of, you know, because they were going to be like God. I mean, it got to such a point where he knew he had to slow them down, like, whoa, slow your roll, you know. And he confuses their languages, like, really, like, you don't think like if suddenly 5 people in a room who are extremely intelligent, one person started speaking Chinese and one Hindu and one American and one English, like that we'd be lost forever? Now, of course, taking it literally, but now think about this. It could be, quite simply, that God introduced these type of dynamics into the world. So you have to remember, when Newton started this scientific revolution, he was attacked by the critics, by the religious people back in the 1600s. And the religious people attacked him. Why? You think, like, what's the big deal? Like, you're formulating laws. The religious people attacked Newton because they said he was embracing determinism. Well, what does that mean? Newton and Galileo, one of the ways they were able to set off the scientific revolution, not just by their geniuses, but the fact that they're like, you know what? The world is like a clock. It's a mechanical clock with all its complexity and its gears and its, you know, because people knew clocks were complex and, you know, they were growing in complexity. He's like, no, the world is like a clock. You just need to seek to understand it. You need to understand the clock, the wheels, the cogwheels, kind of like the world we see it, you know, like the world, even as Christians, we accept it that it's very ordered, you know. It is composed of atoms, and there's electrons and protons, and, you know, there's proteins and there's molecules, and everything is sort of set. But what you don't realize, which obviously Newton and the critics and the religious people in the 1600s, they weren't really, all the scientists were religious, but the scientific critics in the 1600s realized something that we don't even realize. They realized if you truly believe, if majority of us truly believe what we think we believe, then we would realize that eventually men would become like God. If we knew everything, we knew where every atom and every proton, we knew what every amino acid and where it was moving, we would be able to, and this is mathematical, you would be able to see the future. And that's exactly what all those supercomputers do. In order to do a nuclear simulation, you have to literally simulate everything down to the microscopic, nanoscopic level. And what are you doing basically? You're basically being, we don't think of it because we, oh, it's a computer simulation. But what are you doing? You're being like God. You're making an explosion that doesn't exist, and you could see it happening. You could see what's happening. If scientists could see and track the motion of every atom and every molecule in the world in real time on a supercomputer, they would know everything that's going to happen. There would be no free will. Now these concepts are difficult because you don't tie in free will and all this, but just follow along with me if you will. Now you take quantum mechanics, and this is what's disturbed all the scientists, because the scientists, if you were to ask any physicists, right, what separates them? Physicists were very elitist, okay? Physicists were like, J.J. Rutherford, one of very famous 20th century physicists, said, all science is physics. Everything else is stamp collecting, But physicists, if you were to ask them what makes them different, they would say, I can tell you with certainty X, Y, Z. They knew with certainty because they had the equations. They could calculate. They could do the probability. They can do statistics. They had mathematics. Like, they knew. And what they didn't know, it was just a matter of time before they discovered it. With quantum mechanics, there literally is a veil. Like, mathematically, truthfully, in nature. And I just can't help but think to the Tower of Babel and think that, yes, he confused their languages, but God now introduced this into the universe. Or maybe it was always like this, I don't know. But now with quantum mechanics, you need to understand, as much as you don't want to believe it's true, this is one of the reasons to believe it's true, is that it is a literal veil that separates science and man from God. Man can never, ever, ever be God in any which way because of quantum mechanics. Because when you get down to the nitty-gritty, when you get down to the atom, and you have to understand everything that's going on with the smallest pieces to even predict and be like God, the smallest pieces disappear. They're there, but they're not there. They're here, they're there, they're everywhere. I do not like green eggs and ham. This next quote is Einstein towards the end of his life in his memoirs. He says, I have second thoughts. Maybe God is malicious. He spent his whole life going against the grain and trying to come up with a theory that would supersede quantum mechanics, but he could not, And in the end, it grieved him nonetheless to know that the world really did operate this way. The world operates in a way that, yes, it may be hurting your head, but it operates in a way that you could never fully grasp it. A lot of us, even if we thought that we could fully grasp it, we would just assume, hey, Jesus is going to take me out. Jesus is going to take man out before they achieved, immortality. God's going to take people out before we all, achieve these superhuman powers. That's when the rapture is going to happen. Well, maybe so. I'm telling you, we're not going to get there, because we're always going to run into this wall. So here's an overview. This was basically sort of my intro class, my warm-up class. The whole purpose of this class, one of the things I love about this material is that it is one of the few subjects in the world where you can have the luxury of telling people the end of the story, and it doesn't ruin the story for them. Because in the end, this is what happens, along with a whole bunch of other stuff, which is going to be awesome for you to learn about. But I hope to either A, get your appetite so wet to really understand what is going on, and obviously you're realizing you're missing a lot of what you thought you knew about science. There's a lot that you're missing out on that people aren't informing you on. And two, either you're really pissed off and you don't believe me and you just want to see me fail. Either way, I want you to come back to class. I want you to keep listening. If you're watching this video, watch more videos. And that's really the goal. As far as biblical, I did advertise this as a biblical series. But as you can tell, this isn't a Bible study in the traditional sense. Most of the biblical principles are really going to be gleaned once we really get into the heart of what quantum theory is. But as you can also imagine, this stuff is meat. This is like filet mignon. And most of y'all are barely even drinking milk, scientific milk. I can flash a quadratic equation up on the screen and literally see most of your heart rates go up. So that's why we're going to have to work up to that, But there's constantly going to be revelations. And that's why I really want people to participate in the forums. I want people to gain insight. All the revelations I had going through this material, when I shared it with Pastor Joe, he had completely different revelations. Every time I talk with people about this material, and they see different insights that I never saw before. So it's really important that I hear feedback because everyone sees different insights on what really is going on. But for good faith, we'll go through that I sort of thought of. How does what I said today connect with the Bible? Well, let's do something simple. We're going to establish two truths, all right? Two absolute truths. The first one we're all going to agree with, all right? That we are real, that our world is real. Like, touch yourself, like, you're real. Slap yourself, slap your neighbor, you're real. That's the truth. The second truth is you're going to have to put it on my credit, all right? Put it on my credit card, because this you don't believe. But let's accept that there's a truth, that atoms don't exist in reality unless they're observed. And obviously we already went over that there's no way you can observe them without an electron microscope. So it's not like you run around with an electron microscope looking at the world. So by all the means, there is no reality, because there's no way you can consciously observe every atom. So then we go to Occam's razor. Occam's razor is a philosophical principle that means a lot of things, but for all intents and purposes, it states that the simplest explanation tends to be the correct one. So given these two truths, given that both these statements are true, that we are real, that our world is real, and that atoms don't exist in reality unless they are, it should say, consciously observed, what does Occam's razor tell us that the truth is? I'll give you a second to think about it. All right, your time's up. Occam's razor, or if we think about this simply, the only truth that will unify these two lines here of truth is that there must be a supreme consciousness aware of every atom in the entire universe, so that our world, that our universe is real. Now think about that for a second. One thing I find fascinating is that when God boasts about himself and who he is, he's not really humble. Like, let's be honest, Who were you when I made the oceans? Who are you? It's like, I am God, I swear by myself that I am awesome, God is not humble, and, in that aspect, because he is who he is. But think about this. When God says to us in his word that I know every hair on your head is numbered. Now, a theologian could break this down and make, that's metaphorical, or, maybe God, I'm sure he could count all your hairs, but he's not really saying I know about all your hairs. What he's saying is that I know everything about you, and that I love you, But you can see now, it goes much deeper than that. God really does have every hair on your head numbered. Not just that, but he has every cell and every strand of hair numbered. Not just that, but he is aware of every protein in every cell that's in your hair. And not just that, he is aware of every atom in your being. Because if God were not conscious of every atom that you were composed of, the smallest pieces that even comprise everything in this world, if he were not aware of it, if he were not conscious of it, it would cease to be real. The word says God will never leave us nor forsake us. But we can see now that if he were to leave us, if he were to look away, so to speak, to not be conscious of us, we would cease to be. And that concludes Class 1.